In this video, we'll talk about a very important concept called bias and variance. So let us discuss what bias and variance is, and this is very closely related to the concept of underfitting and overfitting, which we discussed in a previous video. Starting with what is bias. Bias is when your model either underpredicts or overpredicts, but never actually gets its predictions right. So that is when a model is called a biased model. So this typically happens with parametric models, which make an inherent assumption around the distribution of data, and sometimes when the data doesn't satisfy those assumptions and we still go ahead with the parametric models, it results in a loose fit model, which is generally biased. So let us take an example and understand bias. So let's say we have a data which is distributed like this. I have taken a small example where I have just one independent variable and I have drawn a plot with the dependent variable. Now you can see this does not follow a linear relationship. Now if I forcefully fit a linear regression line through it, a linear regression line will at best fit a line maybe something like this around the data. Now this will result in a biased model. Now this model will not correctly predict the dependent variable, and hence the predictions will be off. So this is a biased model. Why did this happen? This happened because we fit a parametric model, and the parametric model had an assumption that the data should be linearly related with the dependent variable, whereas this was not the case, and hence it resulted in a biased model. So usually parametric models, they have high bias. Parametric models include linear models, linear regression models, logistic regression, etc. Now, the concept of underfitting is very closely related with bias. When you have a highly biased model, it usually results in underfitting of the model. So for example, in this case, the actual relationship was a little complex. It was at best like a parabola. It was a quadratic relationship, as we can see here. It was a quadratic relationship, but we still went ahead and fit a linear regression line. So hence this is not actually capturing the pattern in the data. It is loosely fitting the pattern present in the data. So we can say that it is an underfit model. It is an underfit model because the actual pattern in the data is a complex one, but what we have fit is a very simple model, so it's underfitting. So high biased models usually underfit the data. Now let us move to the other end. Let us move to variance and see what variance means. Variance is when you take different subsets from the same data and run different models, and the output of the model changes drastically. That means your model has a high variance. It has high variability in the predictions of the same model. So for example, let's say we have a set of data points. Let's say I have 100 data points and we start running models on a subset of the data. Let's say I take 30 data points and I run models. So I run the same model 3 times. Let's say I have a model M and I run it 3 times with different sets of data. These 3 data sets one at a time. And if the output of the 3 models, if they are very different from one another, that means that the model is a high variance model, because there is high variability in the predictions of the model when you change the data points. Please note that the data points are coming from the same data. So it is coming from the same set of data that is given to you, and yet the output changes drastically when you provide different subsets of the same data. So this is a high variance model. This typically happens with flexible models, with tree-based models, which are very flexible and they can take any pattern depending on the data that is given to them. So this usually happens with non-parametric models. Non-parametric models are models which do not make an assumption around the distribution of data. So linear, logistic, these are parametric models which make assumptions around the data, whereas tree-based models, decision tree, random forest, support vector machines, these do not assume any underlying pattern in the data. These are non-parametric models. So non-parametric models are very flexible. They can take any complex shape depending on the data, and these usually have a high variance. The moment you change part of your input or a subset of your input, the output of the model changes drastically. So these are high variance models. An example of this would be, let's say we have points in this way, and if we fit a complex model through it, it might take a very complex shape. So this is a high variance model. The moment you change a few data points, let's say I run the model again with a new set of points. So let me represent the new set of points with the pink color. So if I run the model again with a new set of points, then the model would entirely change its shape. So the model will then maybe move in this way. It will move in this way. So the shape of the model, it changed a lot, and hence it is a high variance model. This usually happens with non-parametric models. Now, high variance is closely related with the concept of overfitting. So as we can see here, these models are very flexible in nature, and hence they usually overfit the data. So if you provide a training data to this model, to a high variance model, it will try to change its shape and become very complex, and that will usually overfit the data that you have. So high variance is usually associated with overfitting. So what is the solution? Both of these is bad. Even high variance model is not good, as well as a high bias model is also not good. So somewhere there's a trade-off between high bias and high variance, and we try to somehow balance the two and stay in the middle. So if we talk about the total error that we have in a model, any model, let's say any model that we are trying to find. So F is a model that we are trying to find. It is composed of three kinds of errors. One is the error that due to bias, one is the error due to variance, and there is one irreducible error. This is the total error in a model. Let me write it ET. So ET is the total error that a model has, and it comprises of three components. One is the error due to bias, the other is the error due to variance, and the third is the irreducible error. Now, a high bias model has a high error due to bias, a high variance model has a high error due to variance, and this error is basically something which we cannot get rid of the irreducible error. This is the noise in the data, and this usually stays always in the data. What we can do is we can try to minimize these two components. So these two components is under our control. These depend on the type of model selected, type of variables that you have selected, the importance of the variables, the feature engineering that you have done, and whatever changes, parameter tuning, whatever you have done basically with your model. So these can be under our control to some extent, but irreducible error is beyond our scope. So this will always be there in your model. Now these two errors, they usually have an inverse relationship. If you try to decrease the error due to bias, the error due to variance usually increases, and vice versa. So it is very difficult to minimize both of them together. There is a sweet spot somewhere in the middle where both of them take a smaller value, and that is what we try to identify. We do that using a process of cross-validation, which we will discuss in a later video. If I have to plot the total errors that we make in the model, so this is how it will look like. This is the distribution of error with respect to the complexity of a model. So the error due to bias, when your model is less complex, so imagine a linear regression model which is not at all complex. In that case, your model will be a biased model. So the error due to bias will be high, so shown by the red line here. The error due to bias is high when your model is less complex, and as the model gets more and more complex, the error due to bias, it starts to reduce, because you start capturing the complex pattern in the data, and the error due to bias, it starts to reduce. But on the other hand, the error due to variance, it starts to increase. So the error due to variance is represented in black color. So initially when your model is very simple, the error due to variance is almost nil, because your model is very simple and it would not change if you change the inputs given to the model. So a linear regression line, for example, is a low variance model. It doesn't change, the equation of the line would not change if you change the inputs to your model, and hence the error is small. But as you move towards a more complex model, so imagine this model that we showed here, the complex shape that we see here, this is a very complex model and it has high variance. So as the complexity increases, the error due to variance increases. So what do we finally choose? The total error is shown by the blue line here, the blue curve. The blue curve shows the total error, and we can see it initially is high when your model has a high bias but low variance, and it starts to decrease, but after some time it starts to increase once again. So this is the sweet spot highlighted in green here. This is what we try to find using various processes, which we'll discuss later. But this is what is a challenge in machine learning, finding that sweet spot where your model is neither highly biased nor highly variance, or when your model does not overfit the data and at the same time it does not underfit the data as well. So this is the trade-off between overfitting and underfitting, or bias and variance, in any supervised machine learning model. We'll talk about this a lot in the later videos of this course.